These are the computed problems for UIT chapter 3, and the first one I'm going to do is number 2. That says, what is the acceleration of a vehicle that changes its velocity from 100 kilometers an hour to a dead stop in 10 seconds? So I'm just going to write here vehicle. Now the acceleration is defined as acceleration equals change of velocity divided by time interval so from what is the acceleration of a vehicle that changes its velocity from 100 kilometers an hour to a dead stop in 10 seconds. So the acceleration is going to be 100 kilometers an hour to a dead stop. So I would have to subtract 0 from that. Now, technically, I wouldn't have to write that down, but I do to show that, well, change of velocity means the difference between the two, and then divide that by the time interval, which is 10 seconds. And when I do that, 100 minus 0 is 100, and 100 divided by 10 is 10. And then the units are kilometers per hour per second, and if I wanted to, I could put the hour and the second together in the denominator. So the acceleration is 10 kilometers per hour per second, and because of course it's a deceleration, and if the car was traveling to the right, that deceleration would be pointing to the left, and if the car would be driving to the left, then that deceleration would be pointing to the right. So a deceleration, where it gets slower, always in the opposite direction of the motion. Okay, the next problem is number 3, which says a ball is thrown straight up with an initial speed of 30 meters per second. So I guess I just call this ball. And initial speed, or initial velocity, (30 meters per second). How high does it go and how long is it in the air, neglecting air resistance? So they want to know how high does it go, so D equals, or H equals, question mark, and how long is it in the air, T equals, question mark. Now all the equations we came across actually involve time. Since I don't know time yet, I cannot calculate what the distance is yet, which means that I actually will determine what the time is first. So let's do that. So here's the ball that is being thrown straight up at 30 meters per second. And we know something about that ball, as there is no air resistance, that after 1 second it will have a speed of only 20 meters per second, because gravity of 10 meters per second squared slows it down, and then another second later it will have a speed of 10 meters per second, and then another second later it will have a speed of 0 meters per second, and that's actually where the highest point is, so I call this here the peak. Now putting that into an equation would be that v, the velocity, equals gravity times time, and on the way down it would do the same thing, 0, 10, 20, 30. So on the way down it would be 10 meters per second squared times 3 seconds equals 30 meters per second. So by symmetry we figure out that the 3 seconds that I have over here on the way down is also 3 seconds on the way up, which means actually that the total time comes out to 6 seconds. Whoops. 6 seconds. There we go. And the time on the way up is 3 seconds, and that's also what I need in order to figure out what the distance is to the peak. Now that we have the time, we can figure out the distance, and actually that can be determined in several ways. One of the equations says that you take the initial velocity, 30 meters per second, you add the final velocity at the peak, 0 meters per second, you divide by 2, and this is in a footnote, this equation, times the time that it takes, which is 3 seconds. And so the distance, of course, is from here to here, where the velocity decreases from 30 to 0, and that's why I use the numbers that I do. And of course, the time between these 2 points is 3 seconds, so 30 over 2 is 15, times 3 is 45 meters. As I said, now that we have the time, we can actually figure that out in 3 different ways. One would be the average velocity times time, and again this here would be the time up. Average velocity between 30 and 0 is of course 15, and then time up is 3 seconds. Of course that also comes out to 45. I'm not writing that down because I already did here earlier, and you have a choice of 3 equations. And the third one would be to say, okay, 1/2 gt squared, and here this is the free fall equation, so we would actually have to look at on the way down. Again, this is by symmetry, so 1/2 times 10 meters per second squared times 3 seconds squared, and when we look at that, 1/2 times 10 is 5, times 3 squared, which is 9, which is going to be again 45 meters, and I guess I will write that down there, 45 meters. Notice the, oh yeah, mainly to show you what happens to the units. On the last one, we have seconds squared here and seconds squared here. They divide each other, remains meters. On the second one, seconds and seconds divide, remains meters. On the first one, as we add meters per second and meters per second, that is meters per second, and then times a second divides the seconds, which is the meters. Okay, next one is number 5, which says, what is the instantaneous velocity of a freely falling object 10 seconds after it is released from a position of rest? What is the average velocity during this 10-second interval? How far will it fall during this time? Okay, I guess I'm just going to call this problem free fall. And we have some kind of object here that's going to fall down for 10 seconds. So t equals 10 seconds. Well, on the first equation, on the first question, what we have to use is, what is instantaneous velocity? V equals g times t. So we have 10 meters per second squared times 10 seconds. So we have 100. And then one of the seconds divides, so this second is gone, and one of these 2 seconds is gone, or one of the second squared is gone, which leaves a second in the denominator, and of course the meter in the numerator. So it's supposed to be a nicer looking m. What is the average velocity, which of course is at the initial velocity, so initial velocity to the final velocity, and divide that by 2. So it's going to be the initial one, it falls from rest, so that's 0, plus the final one is 100 meters per second divided by 2, which comes out to 50 meters per second. Of course, we could have just looked at that and figured that out. How far will it fall? D equals 1/2 gt squared. So that is 1/2 10 meters per second squared times 10 seconds squared. So that is 1/2 times 10 is 5, times 10 squared is 100, so 500. All the seconds are canceling, and we come up with 500 meters. These are the computed problems continued for the chapter on motion. So here's number 8. Apparently about a car. A car travels along a certain road at an average speed of 40 kilometers an hour and returns along the same road at an average speed of 60 kilometers an hour. Calculate the average speed for the round trip. And then it says in parentheses, don't say 50 kilometers an hour. So it goes a certain distance at 40 kilometers an hour. By the way, that's 25 miles per hour. And then on the way back, same distance, except they don't tell us what the distance is, it's 60 kilometers an hour. And that would be in the neighborhood of, a little less than 40 miles per hour. So it's definitely not a race car, but I figured I'd just choose this one here. Okay, notice yet they don't give us what the distance is. So I put a question mark there, but they're asking us to figure out what the average velocity is. So average v equals, and that's actually what they want us to figure out. And actually, I'm just going to use this one here to highlight that. Well, in that case, what I do like to do is actually use a token distance, or just one that I make up, that helps me to figure out this problem. And the distance that I like to make up is 200, whoops, I meant to use a different color, 240 kilometers. Why? Because both the 40 and the 60 divide easily. So on the D equals 240 kilometers, on the way there, that would mean that the time is that it takes is 240 kilometers divided by 40 kilometers an hour. Of course, we can do that in our heads too. That takes 6 hours. On the return trip, that's 240 kilometers divided by 60 kilometers an hour. That's 4 hours. And then, of course, the kilometers divide each other, and that hour that's in the denominator of the denominator goes to the numerator, which also makes sense when we look at time. We need to have that time unit in the numerator. So 6 hours and 4 hours, that means that the total time is 10 hours, and the total distance is, of course, to get there and return, so that's 480 kilometers, and that means that the average velocity is 480 kilometers divided by 10 hours, and that comes out to 48 kilometers an hour. That seems a little surprising. Of course, they warned us in the problem here, but the main reason mathematically why it's not the exact middle between 40 and 60, which would be 50, but something else, in this case 48, is that the 40 and the 60 appear in the denominator, and because of that, the average is not going to be the arithmetic average, which would mean 50, but different. Problem 9, which says, if there were no air drag, how fast would drops fall from a cloud 1 kilometer above the Earth's surface? So I guess call this number 9, and drops. And we have a distance of d equals 1 kilometer. And that says in parentheses, but let that air raindrops experience air drag and fall. Okay, so we have d equals 1 kilometer, or 1,000 meters. And then they're asking for v equals question mark. And then it turns out that each equation that we encounter in this chapter has to contain time, and we don't have time given here, so we can't right away determine velocity. We actually have to determine time first and then do something with that. So that's what we're going to do, and there is a straightforward equation for free fall that says distance equals 1/2 times gt squared, and plug in the numbers of 1,000 meters equals 1/2 times 10 meters per second squared times time squared. And here we solve for time arithmetically, and the algebra for that equation is already done in the chapter. It's t equals the distance times 2, so that's the 1/2 from the other side, goes to that side, divide by gravity, and of course to get, so the 10 goes down here, and then you need to get rid of the square here, so that's where the square root comes in from. And as I said, that's already given in the book. 2 times 1,000 meters divide by 10 meters per second squared. 1,000 divided by 10 is 100, times 2 is 200, square root of 200, do that on the side, you come up with 14 point something. I round it to 14. And then it's meters divides meters, and then the second squared in the numerator of the denominator appears in the numerator. Take the square root of second squared, that's just seconds. So 14 seconds, and now we're ready to determine what the velocity is. Velocity at the end is going to be g times time without air resistance, so 10 meters per second squared times 14 seconds comes out to 140, and then one of the seconds divides, so it's 140 meters per second. And multiplied that by a conversion factor of about 2.2, going from meters per second to miles per hour, comes out to roughly 300 miles an hour. And so that's what they say. Be glad that raindrops experience air drag. Number 10. This is about an athlete. I guess kind of looks like an athlete to us. So surprisingly, very few athletes can jump more than 2 feet, which is 0.6 meters straight up. Use d equals 1/2 gt squared and solve for the time one spends moving upward in a 2-foot vertical jump. Then double it for the hang time, the time one's feet are off the ground. So we're going to start with d equals 1/2 gt squared, and solving for t is already done for us in the book. And again, it's going to be get the 1/2 to the other side, which means multiply by 2, so 2d, divide by g, so that goes to the bottom, and then take the square root on the other side, and that isolates the t. And now we're going to plug in what they gave us, 2 times 0.6 meters, divide by 10 meters per second squared, take the square root of that. Okay, 2 times 0.6 is 1.2, divide by 10 is 0.12, and now I have to take the square root of that, and the square root of 0.12 is a rounded 0.35, and now I divide the meters, the second square denominator of the denominator, go to the top, and then I take the square root of the second squared, which comes up with the correct unit, seconds. And then for the total hang time, they say double that time, so 2 times 0.35 is 0.70 seconds. And the reason is that this one here is the free fall equation, which means it's from the peak falling down, respectively symmetrically. It's on the way up the same amount of time, but because it happens twice, down and up, that's why we double that.
This object here has a speed of, right there, 100 meters per second. And I'm going to turn gravity actually off. There we go. And I shoot it to the right. And I try to stop it as close as possible to 1 second. There it is. Okay, it didn't quite make it. After 1.073 seconds, starting over here at 0, it has reached just past 100 meters. I did post the actual distance it covered, 107.250 meters, and we can see that therefore it covered 100 meters per second. Okay, so let's start over. This time I'm going to turn gravity on. There we go. I'm going to do the same thing. Of course, now it's going to fall. And again, I'm going to try to stop it right next to 1 second. Let's see. Okay, a little bit more. 1.105 seconds. We see it's around 110 meters here. So 110.5 meters in 1.105 seconds means it still goes 100 meters per second. So no matter if gravity's turned on or if it's turned off, in the horizontal, that object will go 100 meters after 1 second. Okay, again I'm going to reset. This time I'm going to shoot it straight up, and once again I will turn gravity off. I'm going to put it at the 0 mark here, and I'm going to double check if I just changed that, yep, to exactly 100 meters per second. And as I said, I will turn gravity off. There we go. And I'm going to shoot it again close to 1 second. Okay, a little bit short. I don't think I'll make it exactly. Oh, there, just a little bit more. Okay, so at 1.109 seconds, it has gone up 110.95 meters, which means without gravity, we can compare these two numbers, it makes 100 meters per second. Now I'm going to turn gravity on. Reset, turn gravity on. Now at the same time that it's going to go up 100 meters, it will also fall a certain distance due to gravity. In fact, if this object here has no speed at all, and so it's just going to fall under the influence of gravity. Here we go. After 1 second, oh, that was as close as I possibly could get, negative 6.350 meters. I'm going to try it again. Okay, I'm sure that's how close I can get. So negative 4.416 meters after 0.949 seconds, to show here that it has actually, that it would fall 4.9 meters, which is 1/2 times 9.8 times 1 second squared. It's just too tough for me, and respectively, it's tough to see that indeed is the case. In any case, though, I have to click on the object and put it back at a speed of 100 meters per second. In any case, as it's going up at a speed of 100 meters per second and falling down at the same time, trying to fall down, gravity trying to pull it down by those 4.9 meters after 1 second, however, before I click the run button, I have to slow this applet down, the software, make this more accurate. That means that the time is much slower now, because I need to really hit it on 1 second, or as close as I possibly can get. So here we go. Notice that it's a whole lot slower because I did slow it down. And I try to hit the stop button at just 1 second. Let's see if I can do that. Okay, try getting a little closer. Okay, I don't think I get it any better. Notice that it went up 0.979 seconds, but it didn't make 97.9 meters, as if it was going 100 meters per second, because gravity slowed it down. So it's a little bit less. Let's see if I can get even closer. I don't know. Yep, see now it's at 1.024 seconds. It's still not at 100 meters because gravity slowed it down. I'm going to try it one more time. Earlier in my trial run, I did actually come up with 0.999 seconds, and it pretty much was on the 95 meter mark. So let's see. So going up at 100 meters per second originally, but gravity already had slowed it down. Okay. Yeah, I don't think I get any better than that. So after 1.013 seconds, it has only made 96.304 meters because it cannot make 100 meters anymore because gravity is starting to pull it down as soon as it went up.